When I was researching for my previous video where I explained about the notice theorem, I encountered a problem.
Consider this falling object. It speeds up as it falls at a particular rate. Now, I can drop this today or 50 years from now on, and the result still looks the same. That is what we call the time invariance. According to the notice theorem, this symmetry gives us the law of conservation of energy, which means the total energy of the system is conserved. But what if we think on a cosmic timescale? Are the laws of physics actually unchanging in time? In general relativity, Einstein showed that the space-time is dynamic. Just like a sheet of fabric, space-time can curve, ripple, and expand. If space-time itself is changing, then the laws of physics will change over time. So, the continuous time symmetry is broken and the energy is no longer conserved. This is the case for an expanding universe. As space expands, it stretches any photons traveling through it. This is a cosmological redshift, which is different to the Doppler redshift. With Doppler redshift, the light is stretched due to the object moving away, but this happens as the light leaves the object. Once the light is traveling, its wavelength does not change. Of course, assuming that the space it is traveling through is not expanding. With cosmological redshift, on the other hand, the space through which the photon is traveling is expanding and continually stretching the wavelength. This means that the wavelength gets longer, more redshifted as it travels.
And a lower wavelength means a lower frequency. Energy of a photon equals the Planck's constant times the frequency. So as the wavelength gets stretched, its energy decreases. So the energy of a photon traveling through expanding space is continually decreasing.
How to explain whether this energy is just lost or becomes gravitational potential energy is the hard part. Scientists are still debating about this problem.
And the opposite happens to dark energy. Dark energy is also known as the cosmological constant, which is simply the energy density, or energy per unit volume. If the universe expands, volume increases, which means the energy must go up to keep the density constant. Therefore, energy can be created.
But doesn't the energy loss and gain balance each other out? No, because dark energy increases at a much higher rate than the energy lost from redshift, resulting in a net energy gain. Therefore, in Einstein's universe, the energy conservation exists only as a special case. For me, it is a reminder that our understanding of the universe is never perfect. What we initially believe to be true can just be a special case on a larger scale. So keep in mind that there is always more to the story. Actually, before you go, I just want you to have a think about this question. What makes a scientific law a law? If there are exceptions to a law, should we still call it a law? How many exceptions should there be until it is no longer considered as a scientific law? Karl Popper, a philosopher, argued that the test of whether a theory was truly scientific was that it was capable of being falsified. To what extent do you agree?